So hello everyone, welcome to today's introductory lecture about logic gates, logic circuit gates. So firstly, we know there are some basic gates that we need to learn first. So the first gate is, there are three kinds of basic gates actually. So if you have worked with it in previously in any point of time, you have seen that these look like ICs. But now, since we are going to learn using one software which is known as multisim, so we will check how we can design this overall every gate. So one by one we are going to learn how the gates are supposed to be designed. So the first gate is, let's say, first basic gate is known as NOT gate. So NOT gate has a logical symbol of like this, a triangle and a bubble. So here you have the input, let's say A is the input. After passing the input through a NOT gate, the output would be Y equals to A bar. So this Y equals to A bar, you can say this is a Boolean expression of NOT gate. This NOT gate can also be known as inverter, inverter gates. So anyways, NOT gate, inverter gate, whatever you call, you can also call it as complement function, Y equals to A bar. So this function is known as complement function. Now we are going to make a truth table for this particular Y equals to A bar Boolean expression. So since we have our input as A, one input, so our possible combination for this will be 2 to the power n, which means 2 to the power 1. N equals to 1. N equals to 1, which means your input, n stands for the number of inputs. So n equals to 1, which means the possible combination would be 2. So your input is A and your output is Y. So possible combinations for any particular input is either a low input or a high input. So if you have low input, which means inverter will invert the input low into a high output. Similarly, if you have high input, then inverter will invert it or complement it into a lower output as well. So this is the logic overall understanding for our NOT gate. Now if we want to check if it actually works like this or not, we can design it and simulate in a software which is known as multisim. You can use any version. My one is multisim 14, so I will just collect the components so that we can design our circuits. So our first component is obviously to select one input. So what could be the input for our component? So how you can find it? Here you have given all groups, but for finding the source components, we have one group which is sources. So you can select from here. Since we are working with zeros and ones, so we have to select digital sources. From here you can select the interactive digital constant. Perfectly, if you click this after placing this component. So let's place it first, then I will explain. So give OK. So after placing your component, you can easily click on it to make it a 0, which means low input, or a 1 for high input as well. So anyways, our next component would be, again, select component, and then instead of the sources, we have to get back to all groups so that we can find our ICs. We can find our logic gates. So our first logic gate was inverter gate. So you can search from here. Okay, this looks exactly like the logical symbol that I have drawn previously, inverter gate. Okay, so select OK and then just select whichever series you want to work with. Let's say I want to work with the A series. So you can connect it directly or a little bit away. It's totally up to you. No worries about that. Since I need only one inverter, I have already taken it. Next I need one indicator, which means one output. So indicator, you can select lamp like this or maybe buzzer. It depends on different circuits actually. Okay, there are different types of indicators you can select, but for now, since we are learning from the basic, actually in labs when you implement this kind of circuits, you're given a trainer board. You're also given some LED lights for checking that your circuit is working or not, if you are getting adequate desired result or not. So for that, what we can do, we can use our LED. Instead of using LED light, we can just select this one. Okay, so now since we have our probe, this is known as a probe, but after connecting the circuit, you will see whenever we are giving our inputs 0 or 1, depending on that, the light will glow up or it will glow, it will be off. That's it. Okay, so you can select any color. Let's say I'm selecting blue color for now, so I can just place it here nearby. And now since our components are collected, for this probe there is one advantage: you don't need to connect any ground connection or something like that in the simulation. But in real life, when you are making any circuit, make sure you use the ground and appropriate VCC for input, digital input switches for giving the inputs. So anyways, there are multiple videos. If you go through some videos, if you just search in the Google engine, okay, search engine, that hardware circuit for inverter or hardware circuit for any other gate. Okay, we will be learning all the gates. Okay, basic gates. There are different kinds of gates actually, so we will be learning all the different kinds of gates. So by default, as you can see, the light is glowing up. Okay, so as I was saying, let me continue what I was saying. So I was just saying that if you search the name of the gate, then you will get multiple hardware connections. If you search simulation also, you will get different videos or articles, write-ups, different websites containing so many things already. So many things are already available in the internet. But if you want, you can also learn through simulation as well. So anyways, this is our by default. We have not done simulation or checking of the results yet. So in order to check the results, you need to play. Okay, you need to give this run function, or if you want, you can select from simulate and select this one as well. Both will work. Okay, same functionality. So according to our truth table, if you remember, when you had high input, the inverter was supposed to be off, isn't it? Similarly, if you have low input, then you can see the inverter was supposed to be showing high output, so the light is glowing up. So this was all about our first basic gate, which was NOR gate, not gate. Okay, not, which means inverter. Our first basic gate, which was inverter, not gate. Now let's proceed with our second basic gate, which is AND gate. From the name AND, you can understand it is going to be multiplication operation, multiplication function. Okay, so we will have two inputs, A and B, let's say for example, and the logic symbol for AND gate looks like a capital D. Let's say your output is C. Okay, your input is A and B or XY, any variable you can take. So I am taking XY for now. So how will be the Boolean function or Boolean expression? So expression would be, since it is multiplication, your Boolean expression for AND gate would be XY. So now again you have to consider the possible combinations before creating any truth table. So here we have 2 to the power n. That formula we need to apply again. So n the alphabet N stands for number of inputs. So here you have two inputs, X and Y. Okay, So instead of 2 to the power 1, just like before, we are going to write 2 to the power 2. From now onwards, you will see that all the gates will have 2 inputs each. Okay, whether it's AND gate, whether it's the upcoming, different gates, you will see. So now we can just create our, we can just create our truth table. Okay, so we had 2 inputs, X and Y. So our output was C. So now let's see how many combinations we can take. According to our formula, we have 4 possible combinations of inputs. So we can just place it 0, 0, 0, 1, 1, 0, and then the lastly, okay, last combination 1, 1. So if you place 0, 0 as X and Y, obviously after multiplication you are going to get C equals to 0. If you place 0 and 1 combination for multiplication, the value, the output would also yield as low. Similarly, for 1, 0 combination of X and Y, it will also be low. And the result will be high only if you have both X and Y to be activated, which means high. Okay, if X and Y both are high, then the output will be high. This is for our second basic gate, which was AND gate. So we can check how to design one AND gate from our multisim software as well. So just select place, select component just like before. First you need to select the sources. So just go to digital sources just like the previous circuit, okay, previous design. Select interactive digital constant, okay, and then select OK and place it. So now since we have our 2 sources, next target would be to select our AND gate. Okay, so how you can select the AND gate? Just select all groups from here and search. Okay, AND gate, the IC for AND gate is 7408. Okay, so if you select 7408, it looks exactly like one AND gate logic symbol. Okay, so you can just bring it forward. Okay, next we can collect our indicator just like before. So select indicator, select any color. Let's say I'm selecting green color for now. So you can just connect, and after that we are going to make sure to run the simulation to check our results if it matches with the theory that we have done previously in a separate blank page. So now I will run the simulation. You can see for 0, 0 combination that according to our truth table previously, our output was supposed to be low. If we have 1, 0 or 0, 1 combination, you can see, okay, if we take 1, 1 combination, then only the light is high, which means light is on, which means your output is high. If you take 1, 0 combination, again it is low. Okay, so this was all about our AND gate. If you want me to repeat, you can go through the video. You can just play it again and again. So now I will move forward for our next basic gate, which is OR gate. Okay, OR gate. So OR means obviously here also you will have 2 inputs. Let's say your first input is P and the second input is Q. So OR means addition. Instead of a straight D, the OR gate will look like this. Okay, curved D, curved D. So now you can find out your output. Let's say your output is Z. Okay, Z. So the Boolean expression for OR means addition, we already know. this is addition function, logical OR. Okay, so if you write P plus Q, obviously it is addition operation. Since here also you have two inputs, we will follow this particular 2 to the power 2 formula to find our truth table input combination. So the input combination would be, what do you think? Okay, obviously it will be, I hope so you are thinking the same thing that I am also going to do here. Okay, 0 0 0 1. Okay, 1 0. So these things are not that much difficult. These are the very basic introductory tutorials or classes or lectures based on logical gates. So these logical gates will come in handy, it will be the building block for the upcoming circuits. We will see some combinational circuits in the upcoming videos. Okay, I will upload those very soon. I will also try to make some interesting videos for you. So let's see, time is everything. Okay, if I get time, I will make sure to make many videos for you for basic, building the, clearing the concepts, basic concepts. So here we have P plus Q. You can just place the combination of inputs. Let's say if you are placing both P and Q as zeros, so 0 plus 0, obviously the result would be 0. If you place 0 plus 1, P plus Q is 0 1 combination, then due to addition it will be 1. Even if you place 1 0 or 1 1, whatever the combination you place, the result is becoming 1 because you are adding up. Okay, you are just summing up the things. So now we can proceed, try to check this overall operation in the multisim. Okay, so I would like to save it first. Let's save it anywhere. 1 minute. Okay, why not? Why do I have to save it? I don't know. Anyways, so now I would like to show you. Okay, I would like to show you how to design the next one. Okay, next circuit, which was OR gate. Okay, so similarly we are going to collect two inputs for our OR gate. Let's say input number 1, input number 2. Next we are going to select our respective circuit, the respective logic symbol or logic gate. So for OR, actually we know it is 7432. Okay, we will search from here the number, actually number or IC number. So somewhere you will find 7432. I am not able to find it yet. Yes, I can find it here. Okay, 7432, this one. So just you have to scroll, that's it. So just place it, let's say A series like before. Now next, what do we need? We need one probe. Okay, probe, which means our output indicator. So you can take the next color, let's say orange color, and connect. After that, our next target would be to check for the simulation. So connection is quite easy, as you can easily understand. It is just left click. So now we are going to play the simulation. So now it is 0 0 as according to our truth table. If you remember 0 0, our output was supposed to be 0 0 1. Light is going up. 1 1, high output as well. 1 0, high output as well. So these are the basic gates, 3 different basic gates. So if you want to know more about the next gates, let's proceed. Okay, so how to proceed? Let's proceed here. Okay, now we have a clear space where we can draw the next gates. The next gates are known as universal gate. Okay, how many kinds of universal gates are there? One is NAND gate, another is NOR gate. So we can try to understand how the combination for the gates would be. Okay, this is our NAND gate place, let's say. Okay, our first universal gate, and our second universal gate will be NOR. So how does this NAND and NOR look like? NAND is actually not AND. Okay, NAND stands for not AND, which means you're going to design. So why this is universal? There is a reason behind it. You can design basic gates to convert into universal gates. Okay, if you add one NOT gate after AND gate, let's say your input is A, okay, and another input is B, let's say. So your output here will be AB, isn't it, after introducing the AND gate. But when you are introducing a NOT gate here, so what is happening? AB bar, NOT, which means you are complementing your input. So if your input is AB, obviously your output after this introduction of NOT gate would be, complemented, inverted. So AB is the input, the output will be AB bar. So if you want, you can design it this way in the simulation tool. I can show you. So let's try to design it fast. There is another way you can design NAND gate. I will show that to you as well. Okay, so we need our sources first. Okay, so let's say this is our first source and another source. We need what? We need our gate. Okay, so AND gate was 7408. Let's find it from somewhere. Okay, AND gate was 7408, and similarly we need our NOT gate. Okay, so NOT gate is this one. So let's place it. After NOT gate we need our indicator. So let's bring one indicator, let's say red light for example, and just place it. So escape and connect. So now we can check after our connection that whether this circuit is actually working like a NAND gate or not. Okay, so NAND means invert of AND. So if you have AND as 0, 0, 0, 0, 2 inputs you had for AND. If you get the output, for 0, 0, the output will be 0 for AND gate. But due to NAND, which means it is getting inverted, so 0 will be inverted, isn't it? So if you invert 0, you are getting a high. Okay, this is our NAND gate operation. So this is one such example. If you take 0, 1 combination, you can try with different combinations as well. 1, 0, okay, 1, 1 only. So how this is working? We need to check the truth table first, isn't it? So you can also design NAND gate like this. Okay, instead of 2 ICs, this was AND IC and also NOT IC. Instead of AND NOT, you can also have one new IC. It looks like a capital D and a bubble in front. Okay, capital D and a bubble in front, which means C will be equal to directly A, B bar. Okay, so if you place these in a truth table, you will have, since you have 2 inputs, your possible combination would be 0, 0, 0, 1, 1, 0, 1, 1. So now just see your output, okay, would be AB bar, which means 0, 0 bar, which is becoming inverted 1. 0 into 0 bar. Okay, 0 into 1 was supposed to be 0 if you make AB, but since you are making AB bar, so make sure that it is complemented. Similarly for 1, 0 as well, it will be complemented, but for 1, 1. you're multiplying 1 into 1, which means your output is 1. But when you complement it due to NAND gate connection, it will be 0. So this is the situation we have seen earlier in the in our multisim software as well. So now let's try to design it. So let's try to design our NAND gate. Okay. So now we are supposed to bring forward our component. First component is source. Okay. So you need two sources. First source, second source. We need to know the IC number for our NAND gate. So we can go back to our all groups. Okay. Select from here 7400, which looks exactly like one NAND gate. Okay. So select it and place it. Okay, just place it. After placement, you need to add your indicator, which means your output, where you want to connect. Let's say you're collecting the yellow color. Okay, so now just you need to add. Okay, now just you need to add the wires. So wire from here, another wire from here, and just connect. Now you can give your simulation and check for 0 0. Okay, 0 1 1 0. Okay, only for 1 1 you can see the light is off according to our truth table. But if you check the other combinations, your light is always on. This is the case for our NAND gate. Okay. So only for 1 1 combination the light is off. If you take 1 1 combination here also, these two are basically the connections for our NAND gate connection. This is not AND combination, and this one is NAND, directly NAND circuit. Okay, NAND IC. So now we can try to understand the next universal gate, which is NOR gate. Okay, so if you want to try the NOR gate, how it will look like, you can just design it like this: A, B, or let's say MN as our inputs. Okay, MN, and your output would be NOR, which means negative OR. Okay, so OR and not negative OR, not negative OR actually. NOR means not OR. Okay, not OR. So let's say your output is S is equals to M plus N whole bar, isn't it? This is the combination for NOR. So you can again simplify it using one specific NOR gate IC, which is 7402. Okay, 7402. So your expression would be similar. Okay, M plus N whole bar, and your input would be M N. So this inverter just converted into a bubble in front. Okay, that's it. So you can make your truth table as well. Since you have two inputs, your possible combination would be 0 0 0 1 1 0 1 1. So now you can check for your output, which is S, let's say. So 0 0 combination, what will happen? Obviously for OR gate, your output was 0 plus 0 equals to 0, but since you have one complement, so you will have 1 here. Okay, so 0 plus 1 was supposed to be 1 for OR gate, as we have seen previously, but this is invert or complement of OR, which means you will get 0. Okay, this will also be 0, and for two high inputs, OR gate was also high, but you know, for NOR gate the output would be low, inverted. So this is the combination. So you can see only for low inputs, low equal inputs, okay, equal low inputs, you're supposed to get one high output. So we can implement this here as well. Okay, let's try to draw our NOR gates. So similarly we can draw here. Okay, so our first NOR gate, you can draw it in two ways as well. I will just show you fast. Okay, just take the source, you know, two digital inputs. So I need 4 digital inputs, 2 for this sort of previous representation and 2 for the next simple logical direct logic circuit. Okay, so next, how many ICs do we need? Okay, so the first IC would be OR, which means 7432. So it is here. Okay, 7432, you can select and place it here. The IC for NOT gate was supposed to be 7404. Okay, and connect it. So the IC for NOR gate is 7402, this one. So you can bring forward. Okay, bring it here. After that we need 2 probes. Okay, 2 probes, so you can collect from indicators. Probe number 1, let's say yellow red color. Okay, and the other one, let's say yellow color. So now our target would be to connect it only. We just connect. Next is here. Okay, now our target would be to run the simulation. So as you can see, for 0-0 combination the light is on, for 0-1 combination light is off, 1-1 combination off, 1-0 combination as well off. Similarly for this one as well, since it is also working like a NOR gate. Okay, 0-0 light is on, 0-1 light is off. If you take 1-1 combination, your output is off as well. 1-0 combination, output is also off. So this was all about our universal gates and also our basic gates. So last 2 groups of gates are remaining. So you can learn from the next. Here I can draw it. Okay, so first is XOR gate. Okay, 2 gates which are known as exclusive gates. So exclusive gates, how can we design the exclusive gates, or why these are known as exclusive gates? Okay, so there are 2 exclusive gates. One is EXOR. Okay, another is XNOR. So exclusive, why these are known as exclusive? Because these gates can be again divided, or these gates can be designed using the basic gates again, which means all the basic gates. We had 3 basic gates, and or not. Okay, these 3 basic gates can be utilized for designing our XOR or XNOR gates. Okay, so let's try to design our XOR gates. Okay, XOR gate first. So exclusive OR. Okay, so XOR, you can draw it. The gate will look like this. Okay, this is the IC actually. This is for XOR. So you can name the inputs, let's say A, B, the 2 inputs, and their output might be C. So now you might have a question that how we can make our Boolean expression, or the logical function for this XOR. So expression for XOR, C equals to A XOR, there is a special symbol for it, okay, XOR B. This is for XOR, okay, and the next gate will be XNOR. So the Boolean logical symbol, okay, the logical symbol for XNOR would be negative XOR, which means a bubble, okay, not XOR, okay. So your expression would be, if you have AB as your input, then make sure your output is C if we want to. So we can take our combination, since it is not XOR, okay, not XOR, so it will look something like this, okay, clear? So now let's proceed. So we can make our inputs combination A and B. Okay, before making the input combination, we can simplify our Boolean expression. So how does it work? Okay, let's do it. A, B bar plus A bar B. Okay, AB bar plus A bar B. So this is the equation for our XOR. So now let's make the equation for XNOR, which means you are just going to write the same thing, okay, you're just going to write the same thing, but make sure there is one okay, make sure there is one complement over it, okay, this bar complement. So if I want to simplify it, we can do it using the De Morgan's rule, okay. Whenever two components, two variables are being added and have one complement over it, then what we are supposed to do, according to De Morgan's, we are going to simplify it, okay. AB bar, okay, De Morgan states that it has to be multiplication between the two components just by introducing one multiplication and complement above each component, okay. So here is your first component and second component, and there is separate complement over each, okay, complement over this one and complement over this one as well. So now if you want to simplify it, you will have A bar plus B. So again multiply with A plus B bar. I have skipped one step. It was supposed to be A double bar plus B and A bar plus B double bar. So we have a rule actually, B double bar is equivalent to B from Boolean rules, okay, rules of algebra. You can go through this Boolean rules of algebra. If you see that B bar would be equivalent to B, A double bar, B double bar or A double bar, whatever you are taking, any, if you have 2 times complement above any element, then obviously it has to be the same original one, which means A double bar equivalent to A. So now we can cross multiply A dot A bar, okay, plus AB plus B dot B bar plus A bar B bar. So if you apply rules of Boolean here as well, A dot A bar, we know that A dot A bar equals to 0. Similarly, B dot B bar equals to 0. So AB plus A bar B bar. Okay. So this is the final expression for our XNOR. So you can try to make the truth table for XOR and XNOR now. Okay. So AB is our input side, output is C for XOR, and for XNOR it is C bar. Okay. So if you place the combinations here, combinations would be 0 0, 0 1, 1 0, and 1 1. So when you place 0 0 combination here, you're supposed to get 0. You can place it and check. Okay, 0 dot 1 plus 1 dot 0. So whenever 0 and 0 are getting added up, you are getting your XOR output to be low. You can try 0 1 combination, you will get high output, 1 0 high as well, 1 1 0. But if you make C bar, obviously the output is supposed to get inverted, isn't it? So you can try placing 0 0 here. Okay, I can show you one. Okay, let's say A is 0, B is also 0. So A bar is supposed to be 1, B bar is supposed to be 1. So if you sum it up, you are getting 1 plus 0, which is our first condition being satisfied. You can try some other combinations as well, 1 0 or 1 1, you will get the same result. So instead of wasting any time, you can also try to implement this overall combination in the multisim. So let's draw it. Okay, so we are going to select place. Okay, before we place it, we need to make sure that the simulation is off. So we can just collect our component, two indicators, let's say, as output. Okay, one for XOR, another for XNOR. Similarly, we need sources. First, two sources for XOR, okay, and the next two sources for XNOR. Next, we are going to select our gates. Okay, for XOR, the gate number is 7486. Okay, so 7486. Let's search for it. Yes, the last one. Okay, this is the one how XOR gate looks like. So we can select the series, let's say A series, and then just select XNOR gate, which is 746 something. Okay, let's search. Maybe this one. Yes, 7466. So select and place. So now we are just going to connect it. Okay, just connect. Similarly here as well for XNOR gate. Sometimes there is a problem with this XNOR gate. It does work sometimes, it does not work sometimes as well. So if it does not work like this, we are going to try XNOR in a different manner. So let's check. In order to check it, we are going to run the simulation. Let's see. For 0 0, XOR is supposed to be low, so it is low. For 0 1 combination, XOR is supposed to be high according to our truth table previously. If we take 1 1 combination for XOR, it is supposed to be low as well. If we take 1 1 combination, the output is supposed to be high. So XOR gate is being satisfied. Okay, it is logical enough. It does make sense. It matches with our truth table previously. But for XNOR, if you look carefully, for 0 0, our output was supposed to be high, isn't it? But it is showing low. So I already told you beforehand that XNOR does disturb sometimes in simulation also, and also in real life. XNOR gate does not work that much. It helps. It sometimes it works, but sometimes it is not working. So what we can do? So let's check the other combinations, 1 0 or 0 1 combination. Okay, 1 1 combination also low. So it is not satisfying. So what we can do, we can just delete our gate. Okay, just delete it. Okay, we need to stop the simulation in order to make any edits. So delete the gate. Just place your XOR gate. Okay, we will place XOR first, and after that what we can do, we can introduce one NOT gate with XOR. If you make complement of XOR, you can easily see that the result was XNOR, isn't it? We have seen that previously. So we will try to do that here as well. 7404, let's bring. Okay, 7404, and we can just connect it. Just connect the wires. Now we can hope that it might work. Okay, let's try it out. So this is supposed to behave like a XNOR truth table, which means for 1 1 or 0 0 combination only the light is supposed to be activated. Okay, so you can understand for 0 1 combination or 1 0 0 0 it is high. Okay, it is working. 0 1 combination it is low. Let's take 1 1 combination, it is working. If you try 1 0 combination, it is not supposed to work as well, which means output is supposed to be low. So now all our gates are satisfied, all our basic gates, all the different types of logical gates, basic gates, exclusive gates, NAND gates we have already completed. So I hope all of you will be practicing this at home, in your leisure time, or in your office, wherever you are. Okay, you can just practice it in the multisim software and check for the results. In the future videos I will give you some reference. If you don't have the software with you, you can try one website. Okay, multisim live. Okay, multisim live. So I will show you how you can design there as well. So in the next videos you will see those information step by step. So thank you very much those who have seen this video fully right from the start till the end. I hope this will enhance your basic knowledge. Those who have forgotten how the logic gates work, I hope this will help you to build your basic knowledge as well. So thank you very much. Bye bye for now. Okay, and take care. Hope to see you next in the next video again. So take care everyone.